voltage sensitivity coefficients are giving the inverse of the J matrix. So of course we can use one or the other. Important to remember, if you're controlling just the voltage at one node, you may think that you need only the one row of the matrix. But of course, as partial derivatives, as rules are with partial derivatives, even if you're interested in a small set of coefficients, you need to invert the complete matrix. You probably know this, but this is a quick reminder. I move directly, skipping one or two slides, to what is called sequential linear programming. In what we have seen so far, I can approximate the grid state by a linear set of equations. If we do that once, we have something that's very approximate and sometimes is good enough. If we want to be a bit more accurate, we will do that iteratively. So the idea is that we solve a linear problem, which is an approximation. Then that gives us a tentative optimal point, and then we re-linearize the power flow equations at this newly found tentative optimum, and we do it again. So this is called sequential linear programming. So this is the classical method when we have nonlinear problem, we linearize, that gives us an approximation, and then we refine the approximation by linearizing again. So that gives us the second type of second way of solving the OPF practically, called sequential linear programming. Assume the OPF consists in minimizing a cost function that's a function of the voltage magnitudes, the voltage angles, the power injections. Then we will replace the power flow equations by PQ is F of V theta, where this is assume that my optimization problem, my OPF, my true OPF is given in this way. So these are the grid equations, the normal grid equations, plus some linear constraints on voltage and angle and P and Q. So those linear constraints contain, for example, voltage magnitude less than 1, and perhaps also constraints on the injection powers. For example, if an injection power has to be satisfying an exact quantity, that is taken care of. I assume all the constraints here are linear. This is, of course, nonlinear, but with sequential linear programming, we will replace it by a linear approximation, and we'll do that iteratively. So it works as follows. Assume we start from initial points. I mean, all those heuristics method needs an initial point. We take it, for example, or most of the cases by DC OPF. Then, because DC OPF is not exact, that gives me some operating point, an electrical state, V0, which is 1 everywhere, and DC OPF will compute the angles. Then I can compute the exact load flow solution. There are two ways to do it. You can compute P and Q and do a load flow, or use the V theta and compute the P and Q that corresponds. Either ways are possible. And then that gives me an operating point, V theta PQ 0. I compute the load flow Jacobian at this point, and I solve the approximate problem where I've replaced the grid equations by this linearization that we saw a minute ago. That gives me an optimal solution. I call P bar Q bar the optimal solution because the grid equations are approximate. The load flow equations don't hold exactly. In this version of the algorithm, we find V and theta. From V and theta, we derive P and Q. That means we derive them through this approximate equation. But since they are only approximate, the true injected power will not be the correct one. So I correct them by doing again, applying the true grid equations. This is not a load flow. This is the direct computation. That's simple quadratic applications of everything here. That gives me the true power that results in this V theta. Of course, if we do this, we don't have exactly the same optimal point. So the idea is to re-linearize again and iterate and hope that it converges. Sometimes, most of the time it converges. Sometimes it does not. Sometimes it produces values that are oscillating around values. If that oscillates, then we will have values that are approximately optimal, and the V theta will need to, the PQ will need to be derived from V theta in this form here. There is an alternative form, which is exactly the same, but uses PQ as main variables and derive V theta from them. So they are, of course, equivalent in the sense that we will do the correction through an exact load flow, but the numerical is more complicated here. Here, I start taking the approximate solution that I have, but I keep P and Q and I find the exact value of V theta. Why would we do one or the other? Well, it depends what are your constraints. Very often, what we need to do is this one, because very often we have, for example, hard constraints on some P's and Q's. For example, at one bus, the power you want to inject is given. So you cannot have an approximate value of P and Q. You must have the exact value. In that case, you take the exact value that you obtain, you replace your approximate values obtained from DC OPF by an exact solution through a load flow. And then you use the same trick. You linearize around this operating point that you have. That gives you a problem that is now with linear constraints. That gives you a value of P and Q that are exactly satisfying the constraints, and of V of theta that are approximately satisfying the constraints, because it is only the approximations of V and theta that satisfy the linear constraints. So here, if you want to correct for this, you will correct doing a load flow for the V and theta, and you will iterate, hopefully, hoping that it converges. Here, the difference is that if the algorithm doesn't converge, but you stop because you've had enough iterations, you will have values of P and Q that are exactly satisfying the constraints, and a V of theta that are approximately true. And most of the time, that's what we want to do, because the values of V and theta don't need to be known exactly.
There's a question on the chat.
Thank you, Pluton. So SLP isn't very similar to the Newton-Raphson algorithm we used. Yes, SLP is iterative, but the objective is different. In Newton-Raphson, you're trying to find a V theta that satisfies the load flow equation. Here, I'm doing more. So I am doing a load flow at every step with this formulation here. LF means I do a load flow. So here I do an iteration, solve an optimization problem, then do a load flow. So inside this block called LF, I will do iterations with the same J matrix, by the way, that will be computed. And in fact, one way to obtain the J matrix is to ask the Newton-Raphson solver to give me the J matrix, right? So step 4 can be given as a byproduct of load flow step number 7. So yes, there is similarity, but there's more complexity. It's an algorithm that will need to do one load flow at every step, plus iterate on it. But the goal is different. We want to find not one electrical grid that corresponds to one load flow, to one set of power injections, but we want also to find what the power injections should be that satisfy my optimality goal. So if we recap, for example, if we go back to the voltage control problem, here are 2 versions of the voltage control problem. The very first version would be doing minimize the voltage penalty that is given by this, subject to the constraints that are expressed in the form of linear constraints of the grid. If we do this, the problem is, of course, much simpler. I don't need to do a load flow and I don't iterate. But also it is more approximate, because in fact, I'm finding an exact solution to an approximate formulation of my grid. In particular, the P and Q that I will find and the V theta don't exactly satisfy the load flow. So they are not exactly feasible, but if they are close to something feasible, that will be good enough. So that is what is done in typical real-time systems, or systems that will try to correct set points of the grid. They will do it in this form. If you do it once every 5 minutes, for example, then you will try to do something a bit more accurate. So you would do exactly what we said before. So you would compute an optimal solution of the linear approximate problem where the objective function is given by this. And we have seen that such a function can be transformed at the expense of adding additional variables into a linear objective. So we have to solve here a linear program, which is reasonably fast. Then we find things that are probably not exactly satisfying the load flow. So we correct the load flow in one form or the other. Here I took the simplest form until it converges. And even if it does not converge, if I'm giving only a maximum number of steps I want to do, I will in most cases find something that is significantly better than what I have obtained here. Voilà, so that is another type of formulations, and that is what I would say the state of the art today on voltage control and how we use OPF for that. Of course, if we would have a magic exact OPF solver, we would not be embarrassed by all that zoo of approximations. We would simply say, minimize this subject to the exact OPF solution. So perhaps in the future, if there's an exact solver for all problems of all kinds, perhaps with quantum computers, who knows, then we will revisit this. But today, the only thing we can do is really find convexifications, and in particular, sequential linear programming. Voilà, a few questions on sequential linear programming. I close the poll in a few seconds. Closing. The majority says A, but the majority is not always right, even in Switzerland. The solution obtained is not a true minimizer of the AC OPF problem. A true minimizer means we have been able to solve the non-convex OPF, and unfortunately, we're not able. That's a difficult thing to do, other than numerically in small scale or using very, very powerful systems in larger case. So A is not true. But B is true. So we find something that is perhaps not exactly the optimal point, but certainly satisfies the power flows exactly. Because by nature, whatever form of sequential linear programming you use, you correct at every step the approximate solution that you have to make it exact solution of the load flow equations, of the power flow. Load flow means the same here. So it is perhaps not exactly the optimal one, but it is exactly satisfying the power flow equation. Unlike with DC, probably. So that's answer B is the correct one. And with DC OPF, I close the poll in a few seconds. Closing. Majority says D, which is correct. So A is not true. The equations are approximate. So like with SLP, there is no hope it satisfies the exact problem. But B is also true. It gives something that is only approximately physically true. We've seen that power losses, for example, are ignored, and voltage magnitudes are always set to 1. So the power flow equations are not even solved exactly. So that's a major difference between DC OPF and SLP. So SLP is a heuristic to solve something that is exact satisfying the constraints of the AC OPF, but is perhaps not truly the minimum point. That's the main difference. Voilà, now we move to another part of this where I will do a recap on everything we need to know to understand locational marginal prices. We have seen them in the example. They're defined as the increase in cost due to an increase in demand, and that's the ratio of the two here. It's very important in electricity and smart grids because this is used to define what we will see in a few more hours as the demand response, as the supply curves here. And it's defined in some markets to define the cost of electricity when you have variable costs here. And it's computed from Lagrange multipliers. So the topic now is Lagrange multipliers. Probably all of you, certainly most of you, and perhaps all of you have gone through that already. But in my experience teaching this course and also my personal experience struggling with Lagrange multipliers, it's something that is complex because not everyone is using exactly the same assumptions and the same results. So it seems simple, but there are a few details that are important. So to get around this complexity, one technique that I found that works is to use only one's reference book, which is used by many as the best one today, which is Boyd and Vandenberghe's book on optimization for convex problems, which is freely available online and is I have put a link to it on Moodle. That defines a given framework. The framework is what is written here. That's how you can define in a generic form once for all an optimization problem. So we have a function to minimize, so we put always minimum, not max. If you have something to maximize, then you translate into minimizing minus f. The function f has a domain of definition, and that's real values. We don't have integers here. And there are constraints that can be put in two forms. Inequalities, if it's an inequality, we always put it in the form a function less than or equal to 0, otherwise equalities. So that's what I call the standard Boyd and Vandenberghe's form here. This problem is feasible if the set of constraints is not empty. Right? If the problem is infeasible by convention, we say that the minimum value is plus infinity, which is saying the minimum of an empty set is infinite. Right? So those are extreme cases, bad cases here, but bad cases do occur, and you will find them when you try to do optimization with Matlab. Sometimes Matlab will return with something saying the problem is unfeasible or the problem is unbounded. So the first thing that may happen is the set of constraints are not consistent. There's no X that satisfies all the constraints. Another bad thing that can happen is that the problem is unbounded. When you try to find the minimum, the value is in fact minus infinity. So there is no good minimum. You can always find values that are as small as possible. This is when the problem set is such that f is unbounded from below on the problem set. In that case, we say that the optimal value of this problem is minus infinity. So plus infinity when it's not feasible, minus infinity when it's unbounded, and hopefully in most cases we find a finite value here. I will do here, share with you my cheat sheets on duality, so everything we need to know about duality to be equipped once for all in the rest of our lives here. The trick, of course, of all that stuff is to use the Lagrangian and how that relates to dual. So the Lagrangian consists in removing the constraints and putting them in the objective function. At least some of the constraints. So there is a little trick here. When I say the domain of definition of the function f, that may implicitly include some constraints. For example, sometimes we impose x to be non-negative. So when we do the Lagrangian, we have first to decide which constraints we put in this form here and which we keep in the domain of definition. Then all of the constraints we have decided to expose in this form here, we put them into the objective functions. We add to them the sum of all the constraints with multipliers that are called the Lagrange multipliers here. Then there are constraints on the Lagrange multipliers. The Lagrange multipliers that are associated with inequalities must be non-negative, and the others can take any values. This is this kind of thing that leads to complexities. Depending on whether you write a positive or a negative inequality. You will have a lambda that's positive or negative, and not all textbooks do the same thing. This is what makes, at least for me, things complex. I find that by sticking to this standard form here, it makes things once for all always the same. And since this is the best book known so far on optimization, it's a good idea to use this one here. So that's the Lagrangian. And of course, we hope that by solving the Lagrangian instead of this, we have the same optimum. And here we have removed the constraints. The problems in optimization is always the constraints. If we don't have constraints, there's a good practical way to solve an optimization problem by following the gradient. You go in the opposite direction of the gradient by steps that need to be adjusted. And there are many software packages to do that. And I will lead you to a minimum point here. But when there are constraints, you hit the boundary and there are lots of problems. So by removing the constraint, we obtain the Lagrangian, and the hope is that this is equivalent. And most of the time it is for us in practice, but this is the most that we need to understand exactly. For that also, we introduce the dual function. So the dual function of the Lagrangian problem, there is one instance of it. The Lagrangian has one, depends on the Lagrangian multipliers, lambda and nu. So for every fixed value of lambda and nu, I have an unconstrained optimization problem. I have an infinite collection of optimization problems, but are the ones I have by removing the constraints and replacing the objective function by the Lagrangian here. The dual function is a function of the Lagrange multiplier, is defined as the optimum, is defining, as the function g is defining as the optimum value of this problem here. Of course, it is defined only when this problem is bounded, which gives a set of definition for the dual function g. If this returns minus infinity, then we consider that g is not defined at this point here. So for every lambda and nu, I solve this problem. I obtain an optimal value that I call g of lambda and nu. And now I can solve another problem, which consists in maximizing g of lambda and nu. Why we need to do that? Well, it would be too short. I don't have enough time to explain that, but that's the magic of duality and optimization. That's the trick here. If I want to maximize the dual function, I have a problem that in many cases will be equivalent. Of course, the hard thing is to know why this is true. The easy thing is to be able to construct it. We'll do only the easy thing in this course. So the thing to remember is the dual function is obtained as the optimal value of the unconstrained problem. And now I change min into max and I obtain an optimization problem that is called the dual problem here. And then we have first result, one that is always true. The optimal value of the dual problem that I call D is always less than or equal to the optimal value of the first problem, which is called the primal problem here. That's a first result called weak duality, which is not very interesting because we would like to have both equal, but in some cases it is interesting. For example, this is true even if the values are infinite. So it implies in particular that if the dual is unbounded, that gives D is plus infinity. That means that P star is infinite, which means that the first P is also infeasible here. So that's a first result that is not at all obvious and is a first result of duality. But of course, we're interested in the cases where both problems have the same optimal value. And if this is not true, it's called the duality gap. And we want to know when it's zero. And there is one case where it is zero. And this is perhaps the most common way of using Lagrange duality, which is called using a saddle point. To make it short, what do? You have your constraint problem P to solve. In P, there are constraints, and the constraints are embarrassing. You want to get rid of them. So what do? You pick lambda and nu, you keep them open. They are fixed, but you don't fix them. They are fixed in the problem L, but you allow them to have any value, and you solve this optimization problem, which hopefully now is for you easier to solve because it has no constraint. And then you look for values of lambda and nu such that the optimal solution that you have found, that depends now on lambda and nu, satisfies the constraint of the original problem. What are the constraints of the original problem? Well, here is x star, the optimal solution that I've found. Of course, I assume that I'll also have the corresponding lambda. I have found for some lambda and a nu, I have found an x star. Then x, which is what I'm expressing here, I'm saying x star is the solution of the unconstrained problem for this lambda and nu star. And I want that x star is feasible for the problem here. So in some sense, I'm retrofitting the constraint. I'm saying I've solved the unconstrained problem. I have found a solution that does not satisfy the constraint because they are not put here into my unconstrained problem. Therefore, I look now for values of lambda, nu, and x star that are such that the constraints are satisfied here. That will give me equations on lambda, nu, and x. I hope I can solve them. If I can solve, I have satisfied this constraint. Now I need additional conditions here, which are called complementary slackness. Complementary slackness are, well, remember that some of the constraints are inequation. And essentially it's saying that either the inequation are satisfied with equality or the multiplier is zero. You must have one of the two that is always true. If the multiplier is zero, that means this inequality was satisfied strictly, which means I had some slack. I could move around the point, make the inequality a bit less or a bit more strict, and I'm still happy about it. In this case, the Lagrange multiplier can be zero. Otherwise, it has to be positive. So the intuitive thing is I solve for x of the unconstrained problem. I verify that the combination of x, lambda, nu satisfies the constraint, and also I need to satisfy the complementary slackness. If by chance, it's not always true, it does not always happen, but if by chance I'm able to find a solution to this program, then bingo, I have solved my optimization problem, which was the goal. And additionally, if I'm interested, I have found the optimal solution of the dual problem. And I know also that my problem satisfies strong duality, which means that there is a hope of this solution to work only when strong duality works. The combination of optimal point and Lagrange multiplier that I find with this method is called a saddle point of the Lagrange. That's why we call it a saddle point. Again, that's the most common way of solving practically an optimization problem with constraints if you need a hope, where you hope to have a closed form solution. Now there are numerical ways, and one of them that is very famous and very often used is called the Karush Kuhn Tucker condition. Karush Kuhn Tucker conditions are conditions on the derivatives here. So that works. What we said before works even if the functions are not differentiable everywhere, which happens when you have absolute values and max functions like this here. If it's not the case, if they are differentiable everywhere, the objective functions, the constraints, then there are those conditions that here is saying that the gradients of the objective functions plus the linear combinations of the gradients of the constraints must be linearly linked by this equality here. So I write this equation that gives me an equations in x, lambda star, and u star, and I solve it. Now I can solve it using Newton-Raphson or any method for solving numerically nonlinear equations. In addition, I must add the constraint that x star is feasible for p. So x star must satisfy all the constraints and the complementary slackness. So if I find a solution for that, then bingo, like before, I have solved the problem. So that's very commonly used numerically. And when do we have a hope that those methods work? Well, it is when we have problems where strong duality holds. What is strong duality? Where those are cases where we are certain that those conditions that I said before work, in particular, that there is no duality gap. So by using the saddle point or Karush Kuhn Tucker conditions, we are certain to find a solution of the original problem and incidentally, find the optimal Lagrange multiplier, which we will see have some interesting interpretation. So for strong duality to hold, one sufficient condition is that the problem is convex. Unfortunately, it's not sufficient. We need also a small additional constraint qualification, which is complicated. There are zillions of different constraint qualifications, but for us, we will use only those ones, which are called the Slater's condition. The problem must be feasible. If the problem is not feasible, you can have convex problems that are not feasible, but that's a bit embarrassing, but we need to verify that it's feasible. Most of the case, it's easy. Sometimes it's hard. All equality constraints which be affine, that means linear plus constant, which is what we do when we do SLP or DC approximation. And the inequality constraints must be affine or are satisfied strictly by at least one feasible point. So when we do DC approximation or sequential linear programming, we're in this case. So as long as the problem at least has one solution, which is probably true because we've done a linearization, so we've found one point. So we are good, we're in this case. And in that case, strong duality holds. That means you can do whatever method we said before. You can solve for the unconstrained problem and look for a saddle point, and that will exactly give you the solution. Here I'm skipping this. It gives also that if the functions are differentiable, then the Karush Kuhn Tucker conditions will always work, because when strong duality holds, they will exactly work here. So if I have a convex problem where those constraint qualification constraint that I mentioned work, then the only thing you need to do is to find a solution to the Karush Kuhn Tucker condition, and that's equivalent. So you don't need to count on good luck. It's a systematic approach that will work for such problems, which for us are practically all problems that we have when we have convexified the problem. All right, that's a lot of stuff on the cheat sheet. For many of you, this is not new. If it's not new, perhaps it's just revisiting things you've seen already, but in a form that is standard and is helpful. You will be able to exercise that in the labs and in the quiz. But before getting there, I want to say what this leads us to. That's the concept of shadow prices here. So a very interesting interpretation of Lagrange duality. It's not the only one, but an interesting interpretation is that we use it for practically solving problems. But an interesting one is this one. Assume I have an optimization problem of the standard form that I said before, where I consider the right-hand side of my constraints here to be parameters of my problem. So for every value of the vector u and of the vector v, I obtain a problem here. We can interpret this as saying each of the constraints expresses some limitation on resources that I have. So u and v are the resources that I have in my system. And I want to minimize something, so that means I interpret f as a cost. If I want to maximize, I would interpret f as a value function, but here I interpret f as a cost here. For every value of u and v, let me call c of u, v the optimal value of this problem here. Then we have this result. If strong duality holds, if fc is differentiable, if it's not, we have weaker statement, but with subgradients, but let me skip this technicality here. The derivative of the optimal cost with respect to the constraints are given by minus the optimal Lagrange multiplier here. What is the derivative with respect to the constraint? Well, this optimal value here depends on the constraint here. So if this function has a differential, I can compute, at least in theory, the derivative of the optimal cost. So it's not f. That's why I use a different function. It's not the derivative of f. F is a well-known function, but here it's a less well-known function, something we know implicitly by solving the problem. So we don't have, in general, a closed form solution. Other than in the lab, I will have small examples where I have you test all those cheat sheets. But in general, we don't have a closed form expression for C. This is why this result is interesting. It expresses to us that the optimal cost is given by the Lagrange multiplier. Now we have a minus sign. Why do we have? Well, it's because I have this standard form. And this is where this theory is embarrassing. And it's why it's interesting to have a standard form, because different sources of information, different textbooks will use different formulation of the standard problem, and we'll have sometimes a plus sign, sometimes a minus sign. To get rid of this, I propose to stick to the formalism of Boyd and Vandenberghe. And then we have this. Now, how can we interpret this? Well, we say, if I interpret this as a cost of running a system when I have resources U and V, well, it says that if somebody could sell to you an increase of the value of U or V here, which price would you be willing to pay? Well, if somebody sells it to a price that is larger than the lambda I, then if somebody sells it to a price that's smaller than lambda I, then you should take this, because by increasing by this amount, you will be able to increase your optimal value or decrease it by minus lambda I, which is a benefit for you. So if somebody offers an increase at less than lambda I, you should accept it, because you will have a smaller cost. The optimal cost plus the price you paid for this increase in lambda will be less than what you had to pay before. Conversely, if the price is larger than lambda I, you should not buy it, because you pay more for the increase of the resource than the gain you have in the operation of your system. So in some sense, we can view that as the shadow price, the hidden price that this resource has. This resource does not have a price. Perhaps this resource is dictated by physical restrictions of your system. But you know that if somebody would be able to relieve this restriction at a given price, this is a price that you would be willing to pay for it. So that's the classical shadow price interpretation of the Lagrange multipliers. Now, if we go back to the concept of an OPF, assume I cast the OPF in this form here. Of course, when I cast in this form, the U and V are complex formulations that depend on all the quantities of my grid here. For example, if I am interested in the locational marginal price at node 1, that's what we had defined 2 hours ago, at the relative increase of the cost of running the grid when we have a small unit increase of load at node 1. Then if I assume that the U and the V depend on L1, on the parameter L1 of my grid, then this is the partial derivative of the optimal cost with respect to L1. Of course, to get that, there's no use taking the derivative of F. What we need is the derivative of the total optimal value of the complex problem, which includes, in fact, the constraints. And by the result we found before, in fact, this is, by the law of total derivatives, will be given by this, the sum over all the Lagrange multipliers of minus lambda I star du over dL1 here. So that's how locational marginal prices are obtained when we have the convex formulation of the OPF here. I did it for this grid here. For the DC OPF formulation of the grid here, I computed the Lagrange multipliers. So I have obtained here, I have 3 equality constraints. So I have 3 Lagrange multiplier here. And I had a number of inequality constraints. Well, I have the values here. We see that all values are 0, which is very frequently the case. A value of 0 at inequality constraint means that at the optimal point, the inequality is not true. So we find inequality constraints that are true here. And if we go back to which inequality corresponds to which multiplier here, I find that it corresponds to the constraint of P23, the power flow on line 2,3, which is saturated. So that's giving me where when one of my resources is saturated. And here that gives me also the G1 max, which is saying here, at least for this example that's given here, that gives the G1 that is operating at full capacity. Now, if I want to find the locational marginal price of node 1, for example, I need to look at all the constraints where there is L1. So there is L1 in one constraint here with a minus sign. So I take the derivative, which is -1, multiplied by minus the Lagrange multiplier, and that gives me this marginal price here. So this is how we can compute the marginal prices. Of course, there's another way to compute the marginal prices. I can also redo the OPF by adding an epsilon of load at node 1 and compute the difference. And if the epsilon that I add is very small, I will find exactly the same thing. One thing that's easy to test here. I think I just gave the solution of this, so let me skip this, but perhaps move on to, Pluton, I'm just skipping one pole. Thank you. Here are the values of the marginal prices and of the Lagrange multiplier. At which maximum price would you be willing to increase the line capacity of the line 2, 3? I close the poll in a few seconds. And the majority does not know, but there's a tie between A and B. The correct answer is A. Let's see the solution. Well, the marginal cost is given by Lagrange multiplier associated with a constraint. The constraint P2 max. Now we need to zoom onto all those constraints. We see there is one here that corresponds there. Now there was a rescaling here. Because of the rescaling, that gives this. We need to change the unit, and that gives this in franc per megawatt here. We can also, and that's interesting to do it manually by redoing the OPF, where I increase the capacity of the line. So that's the original problem. The max branch flows at 200, 300, 200. I increase it by 1 unit for what the lines of interest. And I see what happens here. So what happens is that we have an increase of course, this generator is saturated. It cannot increase. Generator 2 will increase its capacity, and generator 1 will decrease it. Sorry, generator 2 will increase, and generator 1 will decrease it here. So the power flows will be transformed. The marginal cost is modified here, and the difference between the marginal cost divided by 1 unit here gives exactly the price we had found here. Incidentally, we see that when we change something, the changes are not necessarily monotonic. We've seen here that we were forced to increase one generator and decrease another one. That's because of the power flow constraints on the lines here. So sometimes things are not just, the marginal cost does not necessarily mean that's the cost of the most expensive generator. We need to reallocate the flows, taking into account the flows of the constraints of the grid, and then the solution, even with the DC approximation, can be a bit complex. Voilà, that's all we will do for today. Of course, this is done with a DC approximation. If we wanted to find true marginal cost, we would need to do another round with perhaps sequential linear programming, but that is not for today. For the rest of the week, once you're finished with the lab of the previous module, I invite you to do the quiz, which will help you verify your understanding of this module, and then move on to the lab. The first part of the lab will have a few theory questions associated to duality to make sure everybody starts with a sound ground to do the numerics, and then the numerics will ask you a number of questions for running and planning a grid. Voila, I hope you will enjoy this and the coming weeks. Take care.
Thank you. Bye.
Thank you. Goodbye.
Thanks a lot. Bye bye.